So this is the first lecture of a fairly long mini course, and since the material I'll be talking about is not traditional probability, you can't find essentially any of it in standard probability texts. What I decided to do is to give the first lecture, which will be partly philosophical. I will try to paint a big picture of where the results I'll be talking about belong, how they connect to probability, and a little bit to other domains of mathematics. And then each of you can make a decision whether you want to invest more time and hear how such results are proved and what techniques are involved in proving them. I'm going to start with the statement everybody here knows, the central limit theorem. And I will present a very simple-minded version of it, which can be thought of as a growth model in 0 + 1 dimensions. So these are fancy words, but what I want to draw is a sort of a children's game. You have 1 by 1 little boxes, and these boxes fall from the sky and accumulate on top of each other. So you're building a tower with 1 + 1 boxes. So these boxes come with the random waiting time. And what you want to know is what will happen to the height of your tower as the time gets large. Right? So then the law of large numbers and the central limit theorem, so the law of large numbers and the central limit theorem, I'm going to tell you, as long as your waiting times are not wild, that the height at time t, when t is large, in the first approximation will be linear in t, and in the second approximation will have the size of root t, and the coefficient of the root t will be random and normally distributed. Right? Now, everybody knows that. This is probably the most celebrated statement in probability. What if I try to make this picture two-dimensional? So this is zero-dimensional in space because I only have one point over which I'm building a tower. So now I will try to increase the dimension of the space. I'm going to draw the same table, the baseline, and now I will start building towers at different places of the space. So I have boxes falling from the sky. Let's assume in each column they fall independently and they have independent waiting times with some distribution. So if I just say that, then the picture is going to split in an independent set of children's towers I started with. So that's not a very exciting object. So I need to do something to introduce interaction between different columns. Well, there are more than one way of doing that. Let me try the following. Let me make my little boxes sticky. So when they fall, when they come in touch with any of the boxes with at least one side, they stick. So when this box falls, it's going to stick on the side to the one on top. This introduces interaction between the columns. Your picture will start growing in some not very predictable way. And so what you would like to know is what happens to this random object as time gets large. Right? So there will be some interface that will appear, and it's not very easy to come up with a mathematical framework of proving things, but you can easily put it on a computer. It will take you 15 minutes to run a large simulation like that. And what will happen is that the height function that will now depend on the one space coordinate x and time. In the first approximation will be, maybe I put C3, linear in time, which is reasonable because you have the total number of boxes that falls is linear in time. But then maybe you'll try to look for the fluctuations, and what the computer will soon tell you is that this term here will have the size of t to the 1/3. Well, okay, the computer is going to tell you not 1/3, it's going to tell you 0.332 or something like that, but if you believe in harmony in nature, you know that this is 1/3, right? So then you decide, well, okay, maybe this is a very special model, and you modify it a little bit. For example, you can add stickiness and allow boxes to stick on the corner. Or you say my boxes are so sticky that I can stick two units apart. Or, the imagination is limitless. You can put any sort of a similar model like that. And what you will find is that this t to the 1/3 stays. Why? Well, everybody would like to know, but nobody can prove that. So this t to the 1/3 stays unproved. It's supposed to appear in any similar model of this type, and this sort of two-dimensional central limit theorem should hold, but nobody has any idea how to achieve it. Now then, what is this course about? If I go back to the central limit theorem statement, if we go back in time, in our time, in humanity time, and ask ourselves how people come around to understand the central limit theorem, the very first statement that people, de Moivre in particular, realized is the so-called de Moivre-Laplace central limit theorem, which is to consider a very special way of growing this pile of boxes. The time is discrete, and at each second you decide independently with a flip of a coin whether you add a box or not. So then the probability of growing after a certain time a specific height can be computed explicitly with binomial coefficients. And using Stirling's formula, you can compute that this binomial coefficient approximates the normal distribution. So here is an example of a statement that falls in the broad class of models that I'm trying to describe here that is proved. Okay, so let me try to describe that. Instead of looking at this picture of sticky boxes, which by the way has the name in statistical physics literature of ballistic deposition, I will consider a different growth model. So I'm going to draw my, maybe I'll draw it here. I'm going to draw my random interface not with cubes 1 by 1 or with squares 1 by 1, but tilted by 45 degrees. So this is my interface. It's going to be growing. And the recipe of random growth will be that I'm adding a 1 by 1 box at each local minimum independently with exponential waiting time. With some stretch of imagination, you can think of this as being somewhat similar to that. I have boxes falling from the sky, and different columns interact because, well, I can't add a box here because this column is not good enough. But once there is a box appearing here, I can now put a new one here. Again, the computer will easily tell you that the fluctuations will be of size t to the 1/3. The model also has a nice particle interpretation, which I will try to draw as well. This is going to be a lattice, and I'm going to project pieces of my broken line to the lattice, so the middle of the segments. Whenever I have a segment of slope 1, I'm going to put a hole. And whenever I have a segment of slope -1, I'm going to put a particle. So then these are all holes. These are two particles. And then, so the configuration of particles and holes in the one-dimensional lattice parameterized as a broken line like that. And then the dynamics in terms of particles is easy to formulate. Each particle tries to jump to the right by 1 independently of the others with the exponential weight in time. Now the only problems they encounter is when there is a neighbor in front and they're not allowed to step onto the neighbor. So jumps with the particle right in front are blocked. Nothing happens. So this interacting particle system has a name. It's called totally asymmetric simple exclusion process, fairly long name. Each word means something, but I'm not going to tell you what. It's usually abbreviated as TASEP in order not to pronounce the 5 words. And it's a simple model of cars on the freeway. You can imagine that these are cars moving. And then each car, if the next car is fairly far ahead, has a chance of approaching. Right? You can push the gas pedal and come closer to the car that's in front. It seems like a simple model, but it's actually fairly deep. And here is an example of the result. So here is a theorem. Let me start at time 0 at what is called the step initial condition. So I never spoke about the initial conditions for my growth model so far. They can be different. But again, computer simulations are going to show you that t to the 1/3 stays as long as your initial condition is not random. But to state the actual theorem, I need a specific initial condition. And so the initial condition that I will start with in terms of the random surface will be just a wedge. So my cubes will start accumulating inside the wedge. Or in terms of particles, it's going to be the situation when all the particles are packed on the left. And then there are holes on the right. So when my surface starts growing from such a wedge, then at large time, this picture will melt a little bit. So the cubes will fill actually the undergraph of a parabola. And the statement is the following. If I look at the probability that the height function, which is just going to be the, well, okay, so this is my x, and the interface is going to be the plot of the height function. So the height function at time t, if I subtract a suitable constant that will depend on x multiplied by t, divide by t to the 1/3, less or equal than s. If I take the limit when s goes to infinity, then such a limit exists. And one gets a distribution function which is not the normal distribution. The distribution that appears here is called the Tracy-Whittem GUE distribution. And it appeared for the first time before this theorem appeared. It came up in the study of random matrices. Yes? The limit on t, thank you. Yes, this should be t. This distribution came up in the problem of studying large random matrices which are Hermitian with the Gaussian measure on them, which is basically equivalent to saying that matrix elements, they're real and imaginary parts. If they can be independent, they are statistically independent and Gaussian. So the spectrum of such a matrix follows the semicircle law. And if one looks at the largest eigenvalue, so the maximum of the spectrum of H, and scales it properly, subtracts the mean and divides by variance, then the limiting distribution will be this one. I will have a formula for it later on, but it's much more complicated than the normal. On the other hand, so this is one statement. This was proved by Kurt Johansson in 1998. And then the second statement is that if you choose a different initial condition, which is, so the second statement is that if you choose, is it still visible what I write here? The last row, can you, okay. So if I choose the flat initial condition, which corresponds to taking the initial surface consisting of alternating segments of slope 1 and -1, or equivalently, I have a particle, hole, and so on. So initially here, only the first particle could jump, the rest was blocked. Now here, the evolution can start from any point, right? So then if I write the similar limit theorem, t goes to infinity, p h of xt minus some other constant. Actually, so there was a constant here as well. The variance depends on x as well. So times t, c4 of x t to the 1/3 less or equal to s. And this is, well, you wish it were the same, but it will actually be a different object. It will be a different distribution. That also comes from random matrix theory. The only difference, so this description stays the same, except for h, which was Hermitian here, in this case will be real symmetric. There is a reason why people use 1 and 2 there, and I will tell you later about it. This is called Tracy-Widom GOE distribution. So these are actual results. The second one was proved in joint work of 4 authors recently, well, more recently than that one, and this is 2006. And what it shows is that t to the 1/3 that the computer is showing is indeed there. But not only that, the limiting laws are kind of interesting. The multi-point distribution is actually known in both these cases as well. And it's not that universal, so at least it must depend on something. Right? Now, these results give a general conjecture of how the behavior of a model like that should be described at large t. What it says is that the t to the 1/3 should be here, and what sits here should be either f1 or f2, depending on the global geometry of the picture. If the interface is globally flat, it should be f1. If it's curved as a parabola in the step initial condition, then it should be f2. And at points where they join, there should be something transitional, which is also known. So in a way, this is similar to de Moivre-Laplace theorem. By treating a specific model, we get a prediction at what should be happening in a general situation. Now, of course, we wish to have the honest central limit theorem, but at the moment, it seems far beyond what people can do. So in a way, one could think of the course that I'm going to teach as treatment of such solvable cases, proving something like the Moivre-Laplace theorem. It may seem like too little, but I will try to show you a few other connections now that at least convince me that this is an interesting subject to pursue. Okay, so let me play around with these statements, change the formulation a little bit, and that will give me a transition to other models typically studied in probability and some statements about them. So this is my step initial condition, right? So this is my interface growing. I have little boxes that are being added. At each time moment, I have some interface that's consuming boxes gradually. And so what I can do inside of each box, I can inscribe a number, a random number, which will tell me how much time the interface needs to absorb this box once it came close. Now if I inscribe the waiting time for So then I will get the whole grid filled with random numbers. They will be independent, and in the case of TASEP that I was describing, they will be exponentially distributed. Right? So let me try to get rid of the model of growth. If I know these numbers in advance, is there a way to tell when a particular box is going to be consumed with the interface? Right? So the numbers somehow encode everything. And if you think a little bit, then it's fairly easy to say. So the absorption time can be computed as a maximization problem. This is going to be the maximum over all paths that join the box with coordinates. So let me put the coordinates here. Let's say ij. This is going to be the box with coordinates I and j. It's going to be the maximum over all paths on the lattice going from 1, 1 to ij, like that. And what I need to do is to compute the sum along the path of the numbers that I put in. So I'll call them dij. Now this quantity here is called the last passage percolation time. And the reason for that is that you can imagine that there is something that percolating from here to here. In order to percolate through a box, it takes time dij that inscribed into the box. And you're just counting when the last guy will reach the destination ij when it starts from here. Right? So from the, so getting rid of the growth perspective, what the first theorem there is saying is a limit theorem for the last passage percolation time for this oriented percolation on two-dimensional lattice. The universality considerations, or the wish for central limit theorem, says that the limit theorem should be the same independently of what the distribution of the individual entries is. Everybody believes that to be true. Well, one needs to assume that the tails are not too heavy. One needs a certain amount of moments. 5, I think, is enough. That's the current conjecture. But nobody, again, can come close to proving this statement. There are, however, so I said that that statement is equivalent to putting an exponential distribution in each box. There are other possibilities. And also, there are other solvable cases. So one can prove this type of limit theorem, not just for exponential distribution, but for some others. I'm not going to go through all the cases, but I will mention one, because it will allow me to transition to slightly different random object. So here is another example of a last passage percolation problem that is solvable. If I look at the first quadrant, and if I look at the Poisson process with density 1 in this quadrant, so I have particles that spread out. So now this is a continuous model. I don't have a grid. There are particles there that are spread out uniformly, randomly, according to the two-dimensional Poisson process. And then I'm picking a point here, let's say on the diagonal with 2 equal coordinates theta, theta. And then what I will be interested in is in building paths from 0, 0 to theta, theta that are only allowed to go in the right direction. They will have to be upright paths, so that this is a directed percolation. And I'm interested in finding the path that maximizes the number of points it collects along the way. So how is this related to this problem? Well, if you imagine a grid, and if you imagine a distribution here that very rarely takes value 1 and almost all the time takes value 0, then in the scaling limit you will have a continuous picture where these particles are the locations where my filling number is 1 and everything else is 0. Right? This is sort of a semi-universal object. You can always converge to it as long as your distribution here wants to be 0 all the time, except for some rare occasions. So then if I take, let me denote by L of theta, the maximal number of points I can collect along the way. If I take L of theta, if I subtract 2 theta, as it turns out, and then divide by theta to the power 1/3, same 1/3, I take the probability, and this thing is less or equal to S, the limit when theta goes to infinity, and this is the familiar F2 of S. Sort of expected by universality. This statement was for the first time proved by Mike, Dave, and Johansson in 1998. This constant 2 here is due to Vershik and Kerov and an independent work by Logan and Shep around 1977. And the problem has a long and interesting history. Now, if you look at if I draw a square of size theta by theta, now if I number my points according to their x coordinate, 1, 2, 3, 4, 5, 6, and then I number them according to the y coordinate, this gives me 2 orderings on the same set of points, which is a permutation. It's fairly simple to see that the statement that that is formulated here can be restated without any mention of even probability. This is the statement about the asymptotics of enumerative combinatorics in the following way. Let me look at the symmetric group of n symbols. So this is the group of permutations of the set 1, 2, up to n. Now, each permutation one can write as a sequence of numbers. Let's say this would be a permutation of 5 entries. And when I have a sequence, I can choose an increasing subsequence inside it. For example, 1, 2 is such a subsequence. I can also choose the longest one. In this particular case, if I'm not mistaken, it's going to be 1, 2, 5. This is called the longest increasing subsequence. Then if I think of all my permutations to have equal probabilities of 1 over n factorial, and that statement says that if I take my L, so I will denote the longest increasing subsequence as Ln. Then as a random variable, this Ln, when I subtract 2 roots n and divide by n to the power 1/6, converges to F2. So suddenly the problems that I was talking about got transformed into different domains. The problem of the asymptotic behavior of Ln goes back a long time. The problem was first stated by Stanislav Ulam, one of the fathers of the nuclear bomb. That was after the Manhattan Project. In 1961, he published a book, something like Introduction to Mathematics for Engineers, or some sort of applied book, where he said that he used some computer experiments. You can imagine what computer experiments looked like in 1961, but he may have had access to the best ones, being a part of the Manhattan Project. And so he conjectured that this Ln, actually he conjectured that the expectation behaves as a constant times root n. It took quite a long time to settle the question about the behavior. So this statement here, this is the Black-Dave-Johansson theorem. This is 1998. So this constant was actually proved fairly quick. Well, reasonably quickly. In 1964, Hammersley proved that this is correct even without the expectation. And the exact value of the constant, that's the work of Yershik and Kerem and Logan and Shep a few years after that. Now, why should you care about this problem? Let me just give a sort of a fun connection. Now, many of you took a flight to come to St. Petersburg. So here is an airplane boarding problem. Imagine a simplified airplane with just one seat in each row. So here are the seats. 1, 2, 3, 4, blah, blah, blah. Right? So this is the entrance, and then imagine that there is, of course, a queue of people trying to get to their seats. And then these days, airlines charge for checked baggage, and so everybody has a fairly sizable carry-on, right? And each has a ticket. Maybe this guy has a ticket with number 10. This is number 5, and so on. And so when the door opens, these guys enter. The first guy enters. He goes to the seat number 10 and starts packing this big carry-on into the overhead bin, right? Let's assume it takes 1 minute for the guy to do that. And of course, while that is happening, nobody can pass him, right? So then, well, this guy is lucky because 5 is less than 10. So while this guy is packing, this guy will start packing his. But then if the next one has, let's say, ticket 6, then the 6 has to wait before 5 packs. Now the question is, how long will it take to board the airplane? This is exactly the same question as the question of the asymptotics of the longest increasing subsequence. Because if you think of this set of numbers as a permutation, then the time it will take to board the airplane is exactly the longest increasing subsequence. So when somebody on the airplane asked me what kind of mathematics I'm doing, I had a very good answer. You can actually realize that if you split people that board the airplane into groups, it will make the boarding time longer by the factor of square root of the number of groups. But that makes people happier because they can sit, right, not stand in the queue. And there is actually a guy who tried to sell these types of arguments to airline companies. They were willing to talk, but I don't think they were willing to pay. So. Anyway, okay. So there are other applied questions that can be reduced to the longest increasing subsequence. There is also a sorting algorithm called patience sorting that has memory size required given by longest increasing subsequence, and so on. Now I will move a little further. So you can see that these developments by the theorems that I was citing were happening roughly 10 years, well, maybe already 15 years ago, and so on. There was a certain breakthrough that happened in the end of 90s that allowed for this area to blossom. And in recent couple of years, there is actually a new step that allowed people to access something more general. Let me talk about that a little bit. So as a general principle, if you try to maximize a functional over any set, right, you can think of it as a zero temperature limit of Gibbs measure defined by that energy functional. And we'll write the relation, and then you'll see that this is essentially trivial. Right, so this is what I'm trying to do. The log of the sum x in x e beta h of x. So what I have here is the distribution on all elements of my set, which is in the Gibbs form with h. Well, if you want to bring it to the Gibbs form, you need to change the sign of h, but you can do that without me. So when beta gets large, then clearly the contribution of the h with the large, well, the maximizing one will be overwhelmingly larger than the rest. And so the overwhelming contribution to the sum will come from maximizing x. When you take the log and then divide by beta, you just come back to the h. Right? This is sort of the general principle. Now, in my particular case, when I was talking about percolation, what was happening is that as my capital X, I had the set of all paths from 1, 1 to, let's say, ij. And what I was trying to maximize was the percolation time. So I had the random variables inscribed into each of the boxes. I was summing along the path. That was the energy of the path. And then I was trying to find the maximal path, right? Now, if I use this general principle, what will happen is that I will now have a probability, well, if I normalize, then I will have a probability distribution on paths. Or maybe better to say I will have paths with an energy attached to them according to this formula. Right? In particular, if I had these fill-in numbers inside, then again my h of the path is just the sum of dij's along the path. And maybe I should put here maybe I want to have here the logs of dij, and then the energy of the path is going to be the product of the numbers. So E, the h of the path, is going to be the product of these dij's. So the general picture of when you have some sort of a random medium, you have a path there, and that path collects an energy, and in this way, and you want to study the Gibbs distribution, is known under the general name of directed polymers in random medium. Now, for the first time, an object like that was introduced, well, meaningfully introduced maybe 30 years ago in the framework of the Ising model. So the problem that was studied was the Ising model at low temperature with the domain wall boundary conditions. So when the temperature is low, then there is a path there, and if one wants to study the partition function in that mode, then one is led to studying the Gibbs measure of this form. Now, since then, these directed random polymers found many other applications in physics, mostly because most of the results remained conjectural for a while. Let me, instead of trying to argue as a physicist, let me just tell you about one model that's easy to understand in which such random polymers arise. Imagine that we live on the one-dimensional lattice again, and at each location there is a particle with mass. There may be several particles with mass. This is going to be a non-interacting particle system. You'll see what I mean. So then these particles are going to evolve with time. Now, how they are going to evolve with time? So at time, let's say I'm in discrete time. So at time t, location x, what happens is that the mass gets multiplied by some number that depends on the time and the location. So then the particle divides, and or maybe instead of divides, I'll just write reproduces. So it splits into two identical particles of the same mass, and then one twin moves to the right. So, After multiplication, this dot is going to get either heavier or thinner, depending on what Dij is, whether it's more than 1 or less than 1. And then it's going to produce a twin, and that twin is going to be sent to the other location. This is a model of plankton in the ocean. So what happens is the plankton can either die or procreate depending on the conditions, on the salinity of the water, of the temperature of the water, various other, of the number of whales in the area, and so on. So that is represented by dtx. Okay? And then it also moves somewhat randomly and somewhat slowly. And then it's being represented by this moving. So instead of splitting into twins and moving, I could as well put here the probability 1/2 event of jumping to the right by 1 or staying in the same place. Right? So now, if we try to think reasonably, if these dtx were independent of t, just think of them as dx, then they were basically telling you that there are favorable and unfavorable locations for the plankton to reproduce. Right? There are places where you grow exponentially in mass, and there are places where you die. So after a long time, it's reasonable to imagine that this family of plankton will be very well concentrated. Right? They will be localized at the places where these are the largest ones. And imagine that this now depends on t. And these dtx are independent in t as well. So what happens now is that the location that today was very nice, tomorrow may be just terrible. And that is actually not far from what's happening in the ocean, because the turbulent flows create very quickly changing conditions. And the question is, how would such a system behave at large times? It's a very interesting question, very rich question. And the answer to it is that the localization will still happen. There will be still very sharp peaks happening, except for they will happen with small probabilities. But they will be high enough to influence the behavior of the moments. So what will happen in this situation is that if you try to measure the size of the population using moments, if you use first moment and second moment, you will get totally different answers. And if you try to measure it with probability 1, the answer will be yet another number. Well, it will grow, so okay. So this phenomenon is called intermittency, and it was argued by physicists, actually books are written on the subject, that this phenomenon is responsible for many events in nature. For example, the distribution of mass in the universe is intermittent in the sense that there are high peaks, the galaxies, and the rest is empty. Or if one looks at the magnetogram of the sun, then one sees that the magnetic field is very high at very small locations, and typically it's sort of the same. So it's gray, except for there are very high peaks here and there of different heights. So there are actual equations that describe these things that are similar to this simple situation that I'm trying to describe. So what I'm trying to tell you is that this is a natural model to look at with very few things proven. So let me state the theorem. Yeah?
The reproduction of the particles, does it occur deterministically or also there is some randomness?
No,
so every moment a particle splits into two. So
correct.
Deterministic.
Yes.
So only dtx is random.
Only what?
Only multiplication, dtx.
Yes, so the randomness is in there. You could introduce a randomness here where instead of division of the particles, you would just consider a particle moving to the right with the probability half or staying at the same place. That would eventually, for the expectation, have the same effect as particle dividing and moving deterministically. So first of all, let me say right away that the mass, so the mass at time at tx should be clearly So, okay, so the initial, if I take the initial condition, just one particle of mass 1 at 1. Okay, so everything starts, yeah, please.
But you have multiple particles in one spot.
Yeah, absolutely. It doesn't matter. The particles are not interacting. You can have, on the level of computing, it doesn't matter. And you can think of many little particles or a single one. In the expectation, think of tiny particles sitting everywhere. Okay? In the statement that will eventually happen, which will be the expectation over all possible movements of the particle, the split into the little particles or big particles, and it's not going to matter. Okay. So the quantity of interest that I really wanted to get is the following. It's the sum over all paths from 1, 1 to tx. And then along these paths, I take the product of dij, so this is along the path. So on one hand, I hope it should be clear it ties to this model here. On the other hand, this is really the finite temperature analog of the maximization problem that I talked about. Right? So here is a theorem. So let me call this something. Call it z tx. So let me assume that each of the dij, so they are independent, so they are IIDs with a certain specific distribution. This is a inverse gamma distribution. You take gamma distributed random variable and just invert it. Okay. So then, the probability of z n minus n times a constant divided by n to the third times another constant less or equal to s. The limit when n goes to infinity is the familiar f2 of s. Okay. So what it says is that in distribution, the size of the plankton population is going to behave in the same way as the maximization problem that I started with. Now, this is not the only interesting limit transition that one can take. So first, of course, I should draw your attention to the fact that I'm using a specific probability distribution here. This is the analog of the Laplace theorem. I'm more than confident that I can put any distribution, the statement will remain true. This is the only distribution for which is known how to prove it. And this is actually a very recent result. A joint paper with Ivan Corwin and Daniel Remenick. The proof actually appeared on the archive last week. Another limit that I can take from such a picture. So here I had the grid, and in each location in the grid, I had this inverse gamma distributed random variable. Now I can scale this thing, so that instead of looking at the lattice paths, I'm going to look at the Brownian bridge paths. And the weight of the path that I will have to get, so if this is a Brownian bridge, B of s, then the energy of the path is going to be the integral of e to the power beta times the two-dimensional white noise. So this is ds along the path. Okay. Now this is not a very, not a clearly well-defined object. One can make sense of it, and it's actually a proven fact that such an object arises universally if you take a grid situation and then you scale it so that the random walk scales to the Brownian motion. Now this is sort of halfway to universality. You can first pass through the Brownian object. Right? This also corresponds to the case that your plankton moves according to the Brownian motion. and collects the white noise along the way. So the white noise is the ultimately quickly changing medium, right? So then, okay, so if I denote, so then my Z will now have two.
Sorry,
Yeah. So this is the two-dimensional white noise. Thank you. W dot is the two-dimensional white noise. So if I now take my Z, then actually a rigorous way to define what's happening is to see what equation it satisfies. And the equation it satisfies is the following. This is Laplace Z plus V, well, maybe, okay, plus W dot times Z. This is called stochastic heat equation. You know, if I remove this part, now Laplacian here is one-dimensional, so the equation makes sense in any dimension, but in this particular case, this is one-dimensional. If I kill this part, this is just the heat equation, and this is the random potential, sort of. There are various variants of this equation. If I put the discrete space and the Laplacian will be discrete, this will be called the parabolic Anderson model. And the localization problem for parabolic Anderson in various dimensions has been studied for many years. Now, what the benefit of the approach I'm talking about is that one can take the limit of this case and actually produce. So there is a formula for Z of xt. This is a random variable, so for the distribution, for the delta initial condition. Now, a small remark is that if I substitute, if I take the log, so if I write that Z is equal to e to the u, and this equation will become nonlinear. The equation that one gets will be du over dt is Laplacian u plus gradient u squared. Again, these are one-dimensional, but I'm writing it so that one can think of it in any dimension. Now, this is called Kardar-Parisi-Jean equation. It was introduced by these three physicists in 1986 as a way of describing the growth of surfaces that I started with. Remember, I had this ballistic deposition with little cubes falling. So they actually said that there is some universal scaling in which this equation is supposed to describe that thing. Well, the only difficulty is that defining solution of this equation is very difficult. And well, that never stops physicists, right? They can do things to equations. They can do some sort of renormalization group analysis, and that's how the 1/3 exponent was originally predicted. So from what I was saying is that for some specific initial condition, there is actually now a formula for a solution of this equation, whatever that means. There is a recent progress in understanding rigorously what solutions of such equation, of this particular equation should mean, and that's due to Martin Harrier, but that's not something that I will talk about. Okay, so now let me try to suggest some philosophy. Now, if I were to give a name to the collection of results that I talked about and related ones, I would use the term integrable probability. So what is integrable probability? Well, first of all, integrable refers to something solvable in the sense of formulas. So the cases that I spoke about are solvable in the sense that there are explicit formulas one can write for various quantities. Similarly, in a way to the fact that for the sum of Bernoulli random variables, you can write the distribution using factorials. Now, the formulas are not going to be as easy as factorials. There are still some formulas that can be analyzed. Now, integrable something immediately brings analogies with integrable systems. And that's actually meaningful. So there are several direct connections to integrable systems here. Let me give examples. For example, if I take this F2, right? So the distribution, the Tracy-Whittem distribution that I never explained what it is, right? So if I take this distribution, if I take the second log derivative and extract the square root, then the function that I get will satisfy a second-order nonlinear differential equation. This is actually one of the ways of defining this F2 of S. Well, I haven't defined what the boundary conditions for the initial conditions for the equation should be, but that can be done. And when you write such an equation, it's not even clear that the solution exists. This is not an arbitrary equation. This is an equation that was discovered slightly more than 100 years ago by Paul Penlevé. It's called the second Penlevé equation, and it very much belongs to the theory of integrable systems. It can be solved, although not with explicit formulas, but one can prove that the global solutions exist, that the solutions do not have singularities in the complex plane except for poles, which again is very non-obvious, and so on. Now, another connection is that if I look at the solution of such an equation here, of the stochastic heat equation, and if I take the joint moment, z of x1t blah blah blah, z of xnt, let me call it something, f of x1 through xn t. Okay? So this is now not a random variable. I removed the whole randomness. I averaged over the noise. This is just a function in n space variables and one-time variable. Then it's very easy, well, not very easy, but fairly easy to show that this f satisfies Schrödinger equation. Now it's an n-dimensional Schrödinger equation with the potential, which is the delta potential in the differences of variables. It's not hard to do. Now this has a name. This is called the quantum Bose gas with delta interactions. And it's one of the favorite playing grounds for the integrable systems crowd. So the eigenstates for the operator on the right have been found through what's called beta ansatz back in the 60s. 1963 and 1964, first Lieb and Vinegar, and then Maguire studied the two cases when this plus is actually either plus or minus. These are so-called attractive and repulsive cases. Particles either like each other or not. And the behavior of the system is very different depending on these two cases. And so this equation, in a way, is solvable through the R matrix, the beta ansatz, whatever you like to call it. So there are direct connections to integrable systems. That somewhat justifies the word integrable. But to me, actually, the reason these connections exist is something deeper. Both integrable systems and integrable probability is very sensitive to deformations. Like in analysis or in probability, you can always deform a little bit, and your system is not supposed to change much, right? Now, the statements that I gave here are very rigid. I give a particular distribution to my filling number, this inverse gamma distribution, and if I change it a little bit, I'm dead. I can't do anything. Where does this rigidity come from? The rigidity actually, to me, it seems, comes from representation theory. So both integrable systems and integrable probability are some sort of shadows of the infinite dimensional representation theory. Now, there are enough people doing both integrable probability and integrable systems who don't care about that and prove meaningful statements. And And the representation theoretic picture remains very far behind. It's sort of an algebraic approach to both. But it sort of explains why the rigidity, because the representation theory is a subject where you look for objects with, in a way, extreme amount of symmetries, and they are rigid. There are just 5 Platonic solids in 3 dimensions, right? You can't get out of it. You can't deform them. This is a somewhat, maybe, simplistic analogy, but it shows why you can't move around these distributions in a way. Now, there is something that I like more in integrable probability than integrable systems, which is the following. Integrable systems are somewhat exotic in the world of general PDEs, for example. Integrable PDEs like KDV, they have very nice properties, but these properties are kind of far from generic PDEs. Right? There is a theory of systems close to integrable, of course, and so on, but still this is sort of a nice representative. Now, in probability, these integrable situations deliver really what happens in generic situations. Well, this is conjectural in some cases. In random matrices, by now, this is actually not conjectural. So the integrable cases of random matrices, such as GUE or GOE, deliver something that holds for arbitrary random matrices under some assumptions due to very recent progress of a number of people. And it's very convincing somehow, at least from numerical experiments, that the integrable models deliver something that's common. Okay? Not only that, but if you look at the universality proofs in random matrices, what people would traditionally prove is that in the generic situation you get the same answer as in the integrable situation. And the only way to actually get to the answer is to study the integrable case. All right. So the reason for that sales pitch is that the remaining part of my lectures will be on the integrable cases. Okay? I really can't and don't want to get rid of the representation theoretic background, on one hand. On the other hand, I can't really give a representation theoretic class here. And so the way it will happen is that the interaction with representation theory will happen through the theory of symmetric functions. Now, the theory of symmetric functions is sort of the algebraic apparatus that is used in representation theory for various purposes, but it can be viewed independently. It's just a bunch of relations, sometimes miraculous, on symmetric polynomials. Okay. Vadim Gorin, who will teach the TA sessions for this class, will give a crash course on symmetric functions, starting with the next lecture. There is a handout here that summarizes some of the formulas that will be needed for roughly 4th and 5th lectures of my class. But you know, if you really want to understand the background of what really allows one to prove statements like the ones that I talked about, then it's worth looking at least at printout and trying to understand, either read or listen to Vadim what these objects are. I will give definitions, but that will not be sufficient to feel them. Now, the rough plan for the class will be the following. So in the next 2 lectures, I will talk about determinantal point processes. So determinantal point processes is an algebraic formalism of treating certain probability distributions of specific kind. They cover things like GUE and the statements of last passage percolation that I spoke about in the beginning, and TASEP and things like that. So the subject has been developing for the last 10 years or so, and it's in fairly decent shape. I think it's quite well presentable. Now, in lectures, in lecture 4, I will try to explain how the algebraic structures, in particular the structures of something called Schur functions and Schur measures. If you've never seen Schur functions, then really lectures 4 and 5 will be useless unless you go to Vadim's session or read the book on what Schur functions and Schur polynomials are. They are essentially the characters of the irreducible representations of general linear group of a complex field or of the unitary group, but you don't need to know that for what I will be talking about. They're just certain symmetric polynomials with some properties. So I will try to show how the structures of the Schur functions give rise to Markov dynamics that are similar to the exclusion processes that I talked about. Okay. Finally, in lecture 5, that will probably be the fastest of all, I will go beyond the class of determinantal processes into something that we now call McDonald processes. So in that form, so this is related to these objects here, to the polymer, to the random polymers. So the random polymers are not accessible through determinantal techniques. They are not free fermions in physics language. And getting any handle of them requires new considerations. So those new considerations come from these McDonald polynomials that were introduced by McDonald as a unifying object for many of the characters and spherical functions in Rising representation theory. They have remarkable properties. They also give rise to certain integrable systems. And they are the ones that will give the necessary formalism to get to the random polymers. Okay. I hope I'll be able to communicate what replaces the determinantal structure. So the determinantal structure is very useful and when you have it. But when you don't have it, it's unclear what can replace it. And there are certain objects in the McDonald theory that will allow us to get a lot of observables to handle these objects here. And the final sort of general comment is that the material of this class is connected in a non-obvious way to the material of lectures by Grigory Alshansky that will start tomorrow. Essentially, in a way, what he will talk about will be another probabilistic application of representation theoretic structures behind. He will talk about infinite dimensional Markov chains and how one can use integrable structures to actually construct them and deal with them. It's a hard subject, but again, having some integrable structures helps. And if you stay in both, you will be able to see, not immediately, but a little later, you will see that the two things can actually be combined. Okay, so I should maybe apologize for too general discussion, but since this is the kind of discussion you will not see anywhere, the only way to understand the position of the subject in probability and the rest is to hear somebody talk about it. I thought that this may be useful. Okay, thank you.